Here we are with section 1.3, transformations of linear and absolute value functions. So in the previous section, we looked at 4 parent functions, and now we are going to narrow it down and just look at 2, specifically linear and absolute value. In both of those parent functions, we have, remember I was telling you, it's going to be a lot easier if we look at the equation and let the equation tell us what's going on. So here are a few pointers in this whole section. We're going to talk about where to look in the equation and what it's going to tell us. So right here, if I have y equals f of x plus h, well, I know that might be a little bit Greek to you right now. It'll make a little more sense as we get more into this. But on the inside with the x, if I have plus a number, that means I'm going to move to the left. If I have minus a number, I'm going to move to the right. We looked at that just a little bit in the last section, and it's because if I have x plus h and I set that equal to 0, when I subtract h from both sides to solve, that cancels and x is equal to negative h, so my point that I'm going to is a negative point. And the same with this, once I solve x minus h, then if I set that equal to 0, I'm going to get x equals positive h. So it looks like it's kind of backwards. And all throughout these transformations, you will find out, and you will hear me say time after time after time, that anything on the inside, any horizontal translation or transformation, any horizontal transformation, it's going to happen on the inside, and it is opposite what you originally think it should be. So plus is going opposite than we think, which is to the left. Minus is going to go to the right. Now, on the vertical translations, they do exactly what you think they should. So if I have plus k, it is going to go up. If I have minus k, it is going to go down. Any vertical transformation is going to be on the outside. It will not be on the inside with that x value. Alright, so looking at that, let's go ahead and now check out our first example. And it says let f of x equal 2x plus 1. Well, I've got a couple of things going on there. I've got a 2 in front of the x and then plus 1. So this says write a function g whose graph is a translation 3 units down of the graph of f. Well, that means I'm not starting with my parent function here. I'm starting with f of x. So these are some very important steps that you're going to have to make sure that you follow. I want to see these steps written down every single time we work these problems. You must follow them through. We will end up doing this all throughout the year at different times, and we're going to do it the same way every single time. So we're looking at our graph g. So if I start with my g of x function that I am making, it says it is a translation 3 units down. Well, we know from the previous slide that down is on the outside. So if I take that f of x function from right up here, and I'm just going to label it for simplicity's sake, f of x for now, and then I want to take that whole function and move it down 3. So I'm just going to subtract 3 on the outside. That minus 3 on the outside, that's my vertical translation. Now, all I have to do is plug in what the f of x function actually is. So I could take any f of x function and move it down 3 by doing this. Now I know I have this function, so I'm going to plug it in. I'll do that in a different color for you. So we have 2x plus 1 is our f of x. So after that, now we just subtract 3. Well, there are no parentheses or anything like that, so now we can just combine like terms, and I've got g of x equals 2x, and then what is plus 1 minus 3? Well, that's going to come out to negative 2, and there's my equation. And that one was a little short and sweet. There will be some like that, and there might be some that are a little bit longer as well, but just make sure, the big thing is, make sure you follow the right process. Alright, so let's look at another. This one says, write a function h whose graph is a translation 2 units to the left of f. Well, we're still using our same f of x from before, which is 2x plus 1. Okay, now we're writing an h function. So let's write that down. We have h of x, because I'm writing a new function here. And what it told me to do was to take my f of x function, oops, I'm getting ahead of myself here, take my f of x function and move it 2 units to the left. Well, if you go back a couple of slides to that first page we looked at, your left and right movements are inside with the x. So we have f of x, it's left, so that's opposite what we think. We're going to say plus, and we're moving 2 units, so 2. So this is where it might get a little complicated if you're not paying attention and following along, but f of x plus 2, let me put this plus 2 in a different color here so you can keep track of what all we're doing. But this plus 2 is telling me a left movement, so I'm taking this function right here, and instead of f of x, I now have f of x plus 2. All that means is that I'm going to replace every x with my new value of x plus 2. So I have h of x equals, now instead of f of x, I'm using this function, which is 2, and now there's an x right there. Well, instead of that x, I have x plus 2. And then the rest of the function says plus 1. Okay, my colors got a little off there. Let me fix that for you. So we have 2, we have our x plus 2, and then the rest of the function plus 1. There we go. So this x plus 2 in blue here, that's the only new thing, and that's because of that left movement. Now we can simplify. So we have h of x equals, just distribute into your parentheses. So 2 times x is 2x. 2 times 2 is 4, so plus 4. And then there on the end, we still have that plus 1. So now simplify. 4 plus 1 is 5. So we have h of x equals 2x plus 5. And make sure you highlight your answer. Okay, there we go, 2 down. Alright, so we've talked about up and down movements, we've talked about left and right movements, so there's some vertical and some horizontal. Now, let's look at reflections. So reflections is basically, it's a flip. Remember I told you that if you have something on the outside, that is a vertical movement. So if I have a negative on the outside of my function, that's a reflection over the x-axis, because if you flip over the x-axis, it's going to be a vertical movement. Well, if I have a negative right here on the inside with an x, that's a horizontal movement. So that is going to reflect over the y-axis. If it flips this way over the y-axis, that's a horizontal movement. So on the outside, I'm reflecting over the x. The inside, I'm reflecting over the y. Okay? This kind of gives you a better view. Let's look at these graphs real fast. So right here, if I start out with the black line, y equals f of x, then I am flipping it over the x-axis to be negative f of x. Now right here, I have f of x, and I flip it over the y-axis, and I get f of negative x. Okay? Alright, so let's look at example 2. In example 2, let f of x equal the absolute value of x plus 3 plus 1. A says, write a function g whose graph is a reflection in the x-axis of the graph of f. Okay, so there's my key right there, reflection in the x-axis. Now, I left this worded just as it was worded in the book, and it says reflection in the x-axis. If I say it, instead of just reading it, I'll say reflection on or over the x-axis, but just know that that means the same thing, reflection in the x-axis. So now I'm trying to write a function just like I did before. I'm writing a function g, so I'm going to start with g of x. I've just got this one thing going on here, and it's a reflection on the x-axis. So remember, if you're reflecting in the x-axis, then you are going to put a negative on the outside. And that's going to be on the outside of my f of x function. So now all that's left to do is put that negative sign for my g of x on the outside of the entire f of x function, which is the absolute value of x plus 3 plus 1. Now I'll make my 1 look a little different here just to make sure we understand the difference between the absolute value bars and the 1s. So now don't let that little negative sign get lost. Don't forget about it. We still have to distribute. But the absolute value bars, they are, you could think of them as gel bars. You cannot distribute into gel. You can't distribute anything inside those bars. So instead of distributing into those bars, I'm going to keep that negative right there on the outside of those bars. So I have the absolute value of x plus 3, but I've distributed to that part. Now I have to still distribute to that 1 on the end. Well, a negative times a positive is a negative, and then there's the 1 there. So now that's totally complete. I have negative absolute value of x plus 3 minus 1, and that will show me a reflection across the x-axis. Make sure you highlight your answer. Okay? Let's now look at example 2b. So we want to write a function h that is a reflection in the y-axis. So we're getting a little bit of both, just so you can see how to handle each of those. Let me rewrite our f of x function here. It is the absolute value of x plus 3 and then plus 1 on the end. So I'm writing a new function. My new function is an h of x equals, and it says now a reflection in the y-axis. Well, so think back, a couple of slides back, we said that if you have a reflection in the y-axis, that negative is on the inside. So I'm going to have f of negative x. So just like before, I'm going to rewrite this whole f of x function, but in each place where there was an x before, now I'm going to put a negative x. So we have h of x equals, let's go ahead and start writing our f of x function. So that's absolute value of, remember, instead of x, I have negative x plus 3, close the absolute value, plus 1. That's actually all there is to do with that one, because I cannot distribute anymore. I have only multiplied the negative by the x. I haven't changed anything else. So that right there is my answer. That's probably one of the simpler problems that we'll see, as long as you remember how to put your negative into the new function. Okay, there we go. Now, let's look at something else here. Another transformation is going to be a horizontal stretch or shrink. This is very, very important to pay attention to, excuse me. Very important here. So if I have my function that says y equals f of a times x, this a right here is what we're looking at. Remember, the a is on the inside, so that must be a horizontal movement of some kind. So if it's multiplied on the inside, it's a stretch or shrink. Remember, like I said at the beginning, any movement on the inside is opposite of what we originally think. So if that a is greater than 1, it is a horizontal shrink by a factor of 1 over a. So when I write down by a factor of, I have to flip it to be 1 over a. Then if my a is between 0 and 1, for example, 1/2, that is a horizontal stretch by a factor of 1 over a, which would be by a factor of 2. So bigger than 1, this could be 4, and that would be by a factor of 1 over 4, just to give you a little example there. All right, also, let's look at vertical now. Our vertical stretch and shrink is going to be on the outside because any vertical movement is on the outside of my function. Just like with a building, if you're going to climb the side of a building, you're going to go vertically up the wall, it's going to be easier to do that on the outside because on the inside of the wall, there's the floors, there's everything happening, and you're not going to go exactly vertical. On the outside, you could use a rope or a ladder, but you could go directly vertical up that wall. Usually, our horizontal movements in a building are going to be down a hallway or something like that, and that's on the inside. So that's just another way that you can kind of remember your vertical and horizontal movements. So now, vertical, it is what it is. It's exactly as it seems. A greater than 1, so let's say 5. It's a vertical stretch by a factor of a, so by a factor of 5. If I have between 0 and 1, so let's say 1/3, it is a vertical shrink by a factor of a, so that is by 1/3. Vertical, it's open, it is as it is. Horizontal is the one that gets mixed around a little bit. Okay, so let's put that to work. Let's look here at example 3. So here we have problem A. Write a function g whose graph is a horizontal shrink. So let's make sure we make note of that. A horizontal shrink of the graph of f by a factor of 1/3. Okay, so here's where it comes in that this kind of may get a little tricky, but you've really got to pay attention. Because remember with the horizontal shrink and stretch, they are opposite than what you think. So if it says a factor of 1/3, then that is my 1 over a. So if I have 1 over a is 1 over 3, I can make that equal. Then that tells me that my a is equal to 3. So this is horizontal, so it's going to go in on the inside. I'm writing a new function, g. So now I have g of x equals f of, because it's horizontal, so it's going to go on the inside, f of 3 times x. So any x from the previous problem is going to now change to 3x. And that's all I'm doing because that's the only transformation I have. So let's go ahead and plug that into my old function. I've got g of x equals my f of x function. Originally, I have absolute value. Instead of x, I now have 3 times x, and then minus 3, close the absolute value, minus 5. There's nothing to multiply it by. There's nothing to simplify. I have my answer. Some are really simple, some you have to work out a little more. All right, now let's go look at B. On example 3b, it says a function h whose graph is a vertical stretch of the graph of f by a factor of 2. Since it is vertical, my 2 is my a. So a equals 2. I'm good to go. Remember that vertical stretch or shrink is on the outside of the function. So if I'm starting with a new function, h of x, I'm going to take that 2 and put it on the outside of my old f of x function. Stretches and shrinks are multiplied, so 2 times f of x. So now there's going to be a little more work with this one. I have h of x equals 2 times. Now we're going to write down that entire problem from before, which is the absolute value of x minus 3, close the absolute value, minus 5. That's that f of x from that previous problem. So now we just have to distribute. Just like in a couple of problems ago, we cannot distribute inside an absolute value. So we have here h of x equals, I can take this 2 and multiply it by my absolute value. So I have 2 times the absolute value of x minus 3, but I cannot put that 2 on the inside. Then I'm going to multiply this 2 by this 5 on the end. So I have my minus, and then 2 times 5 is 10. And that's all I can do, because I've simplified everything. And there's my new function. It is a vertical stretch by a factor of 2. Okay? I know this video is really long. I do apologize. We only have 2 more examples, and then we will be done. All right, example 4. Let the graph of G be a vertical shrink by a factor of 0.25, followed by, big thing there, followed by a translation 3 units up of the graph of f of x equals x. Write a rule for G. Okay, so we have 2 things going on here. If I want to finish with G, I have to start with something else. So let's go up here, and if we're starting with a vertical shrink, we're going to call that my h of x. And then after, this is followed by this, so then my g of x will take into account that 3 units up. So let's start with h, because I have 2 things going on. So my h of x is the vertical shrink by a factor of 0.25. Vertical is on the outside, and that means that my a equals 0.25. So I have 0.25 times my f of x function. So on this one, the f of x function is super simple. It's just an x. So all I have to do is plug that in. I have h of x equals 0.25, and then there's my f of x, which is just x. That step 1 is done. So we need to label this over here. That's step 1. From right up here, step 1. Now, g of x is going to be our step 2. So now right here we can go g of x. G of x is a continuation, so now I'm having to use h, not f. So it says I'm going 3 units up, so I'm going to take my h of x, and 3 units up is going to add 3 on the outside, so plus 3. Okay, So now all I have to do is plug in my h of x function. So g of x equals, my h of x was 0.25x, and then I have my plus 3 on the end. And there's nothing to simplify. There's nothing I can do there. So there's my answer. And if you need this labeled out to the side right here, this part right here was step 2. All right? Example 5. Right here, write a function g whose graph is a horizontal stretch of the graph of f of x equals the absolute value of x by a factor of 3, followed by a reflection in the y-axis. So again, there's two things going on. The first one, horizontal stretch by a factor of 3. That's going to be 1. Then the second one, reflection in the y-axis. That's going to be 2. Maybe I should write that in there. There we go. There we go. All right, so let's start off. We are writing a function g, so we're going to start with h. So we have h of x equals horizontal stretch by a factor of 3. So if 3 is equal to 1 over a, then a is equal to 1 over 3. So I just have to flip it around. Let me move that over to the side so it's not all in our way. Okay. So if I have h of x, I'm doing a horizontal stretch by a factor of 3. So I have f of, because horizontal is on the inside, f of 1/3 times x. Now all I need to do is plug it in. So h of x equals, my f of x is absolute value, and now instead of x I have 1/3 x. Okay, there's my step 1. Now going to step 2, reflection in the y-axis. So reflection in the y-axis, that is another horizontal movement, so it's going to go in the inside. So I will have, now my g of x is going to be my h of x with a negative on the inside. So negative times the x value. All right, so let's go plug that in. If I have g of x equals, h of x is this absolute value right here. So I have the absolute value of 1/3 times my negative x. I can't leave it like that though. I have 1/3 times negative x. That's going to mean I have negative 1/3 x. So I've got g of x equals the absolute value of negative 1/3 x, close the absolute value, and there we go. All right, let's see, that was example 5. That's all of it. That is all of section 1.3. Finally, sorry it's so long, almost 30-minute video. All right, maybe we can split it up into 2.